Okay, you ready for lesson 2? This has got fewer pages than last time, so hopefully it won't take 4 parts. I really kind of got tired when I made that last video. I'm sure you got tired watching it. Okay, how many? This is kind of review. Not a whole lot of. Yeah, there's a lot of repeat actually throughout the unit. So hopefully that's good. See, independent events. We've already kind of talked about that. All right, so using these letters, how many 5-letter arrangements? And again, that's like a code word where it does matter which one comes first, second, third. If letters can be repeated. All right, so there's 8 choices for the first letter. And since they can be repeated, I still got 8 choices every time there's a new letter. So that's 8 like that. I'll put the answers in later, but this is simply 8 to the 5th power. If no letters can be repeated, then I got 8 choices for the first letter, but after I choose that, I get 1 less choice each time. So that's going to be far less. No letters are repeated, and the second letter must be a vowel. Okay, so it seems like it shouldn't be legal to do this, but we're actually going to think about the second letter kind of deciding what that is first. It actually doesn't matter what order we decide these in, right? Because 8 times 7 times 6 times 5 times 4 is the same as 5 times 4 times 8 times 6 times 7. Like you can multiply them in a different order and you get the same total. So I'm actually going to plonk this thing in here first. The second letter must be a vowel. So 1, 2 vowels. There's 2 choices for that. Then I got to fill in these other locations. After I've done this and there's no repeated letters, if I take one of the vowels out, there's only 7 letters left, and then 6, and then 5, and then 4. Then no letters are repeated, and all the letters must be consonants. All right, so there's only 6 consonants up here. So 6, 5, 4, 3. This one I think I actually know in my head. Times 2, I think it's 720, but we'll see. No letters are repeated, so we're going to have this step-down thing. And the first and last letters must be vowels. So again, we'll fill in the first blank first with 2 choices. We'll fill the last blank in with 1 choice. Then after 2 letters are in their places, there's only 6 left, and then 5, and then 4 for the remaining. Okay. No letters are repeated, and the arrangement starts with E. So there's 1 choice for the first thing. You don't really have to put that there, because 1 times 1 is 1. It's not a nice 1. So there's just, there's 1 choice for how to start with an E. And then after that, there's only 7 other letters remaining that aren't E's. Maybe you're laughing at home. Okay, great. And again, I'll put in all these answers later. And notice this is all just counting. This isn't probability really yet. It's just counting. Like these might be the numerators of, maybe this denominator. If no letters are repeated, what's the probability? Here we go. That the random 5-letter arrangement will have a consonant in the middle and a vowel at the end. So consonant in the middle, that's 6. Vowel at the end, that's 2. And those are separate sets, right? So I don't have to worry about, like, there's no overlap between the vowels and the consonants. So I know there's 6 choices for this, 2 choices for that. After that's all done, there's 6 letters left to choose from. I got 6 choices for that, 5 choices for that, 4 choices for that. But I'm leaving this room here because this is a probability question. Out of the denominator, no letters can be repeated. So that's the 8, 7, 6, 5, 4. Okay. Next, I'm going to go to the calculator and I'm going to put all these answers in. And I'll let you see what those are in a brief second for you. Time travel time. Boom, and there's all the answers. Okay, so I was right about the 720. Also, you notice a lot of stuff cancels here, and this happens a lot. You get these little tiny fractions at the end, or tiny reduced kind of nice numbers at the end. Also, another thing you're probably thinking is, hey, I've heard of this before. I know a name for this kind of process, or I know how to do this quickly with some shorthand notation and some other cool mathematical processes that I've learned before. Guess what? That's coming up in a future lesson. So we're getting our head around it a little bit right now, but all that fancy stuff is gonna come later. We're gonna make shortcuts. Okay, but we gotta get conceptual stuff down first. So if you've never heard of that other fancy stuff, I'm not gonna say what it is yet. That's totally fine. We'll get there. Okay, roll 2 6-sided dice. We've done this before. E is the event you get an even number, and I think they mean a sum of an even number. Like this is a sum of 2, this is a sum of 3, this is a sum of 4. And the event T is you get a number divisible by 3. So like your sum is something like 9 or 12. What's the probability of rolling an even number? Okay, so first of all, wait a second. When we're talking about this, we have I keep doing this first. Let's talk about denominator first, right? So the denominator in all these is going to be 36. Unless they say given that. So until they reduce that, it's going to be 36. What's the probability of rolling an even number and then a number divisible? Oh, wait a second. Oh, I had that wrong. So this is 2 6-sided die. They're not talking about the sum. They're talking about the individual rolls of the what the dice are showing, like each not combined. I'm sorry about that. What's the probability of rolling an even number and then a number divisible by 3? So they mean the black one and then the red one. Okay. Even number. Let's multiply these fractions. It is still going to be out of 36 because there's 6 possibilities of the first one and 6 possibilities of the second one. Even number is 3 of those. Divisible by 3 is, well, it's just 3 and 6, so it's just 2 of those. So it's 6 of the 36. We could find them in here if we wanted to. Even number, against this, and a number, oh gosh, and a number divisible by 3. Oh, that's a little bit different. I think they mean one or the other, right? This is and then, and this one's and. So I believe it's like the first one has to be, you know, it could be either this way. It could be that the first one's even and the second one's divisible by 3, or the first one is, just a second. Let me look at the key. Yeah, this is exactly what they mean. Or the first one is divisible by 3, and the second one is the even number. Or both, and that's also fine because they could both be 6. This is going to be just double what they meant before. I was awkwardly worded. I always try to be clear about stuff like that, about the and then, you know. But if it could be interpreted kind of the same way no matter how you think of certain words, then I leave it. But this one was a little bit tricky. I didn't like the way they said that. Was probably the second die is even if you already know the first one is divisible by 3. Well, these two dice are independent. I don't care what the first one did because it has nothing to do with how the second one comes up. So that is still 3 out of 6 because of what I know about independence. Okay. All right, fair 6-sided die is rolled, and a number is recorded. Let E be event the first. Sorry, even number is thrown, and O is the odd number. Find probability of E. This is just one die now. Oh, and we'll talk about this Venn diagram later. Probably that you got even just on the first one, or just on one toss, is half, right? It's 3 of the 6. Odd, also 3 of the 6. Even or odd, well, that's kind of all of them, right? There's no way to miss that one, but this is impossible. There's no way to do that, which is why they're showing this Venn diagram here where the things are separate, because we know there's actually no way to be both. So they just draw that. If you know that at the start when you're drawing your Venn diagram, you can just draw the 2 circles separate. I've also seen Venn diagrams where you start off, you know there's 2 different events, but you don't know how they collide, kind of, or how they overlap. And it could be that you start the Venn diagram this way and then later figure out that there's no intersection. You can put a 0 there too if there's no overlap. And that's what mutually exclusive is. Mutually exclusive is when you got 2 events that cannot both happen at the same time. So they have no outcomes in common, like being even or being odd, or like being a red card and being a red card and being a black card, or being a freshman and being a sophomore. You can't be both those things at the same time. So you can have one or the other, but not both. If it's those type of events, we call that mutually exclusive. And it's nice to know in mutually exclusive because if things are mutually exclusive, we will be able to add them simply. So we'll get to that. Use logic. In other words, like use the context and use the story and use the situation to decide if it's mutually exclusive. Okay. If the events are not mutually exclusive, show that it's not mutually exclusive by saying how it could happen, that both could happen at the same time. Selecting a marble from an urn, it's always an urn. Well, sometimes it's a bag. Selecting a marble from an urn and getting a white marble and a red marble. Well, if the marble's either like all white, it's like a white marble, or it's a red marble, it can't be both. I'm going to type this in here. I mean, I guess we don't know enough about these marbles and if they're swirly white and red, kind of 2-color marbles at the same time. But that's what mutually exclusive is about. Can you have a white marble and a red marble in one marble? That's what that means because we're talking about a marble. That's a little silly. Throwing a die and having the outcome be a multiple of 3 and divisible by 2. Not mutually exclusive because it could be 6. I don't need to have you watch me type that. Yeah, and I don't know why they use the word multiple and divisible. Why did they say divisible by 3 and divisible by 2? Anyway, that's not mutually exclusive because you could be both those things at the same time. Drawing a card from a deck at random and getting a red card and a jack. Well, that's totally possible because it is possible to get a red jack, and I've listed both ways that can happen. Flipping 3 coins and getting all heads and all tails. No, you can't do both those things at the same time because we're talking about one toss here of the 3 coins as the experiment kind of, and you can't get all 3 heads and all 3 tails successfully on the same occurrence. Whereas you can get a red card and a jack on the same occurrence. And this is going to filter into how we can operate with multiple events when they're happening. Just like before when we were talking about independent events, and if events are independent, you can multiply them. Well, if things are mutually exclusive, there's something else we can do. All right, and this is why people can sometimes confuse mutually exclusive and independent, but they're way different things. Mutually exclusive just means they can't happen at the same time. I guess both things make you think like, oh, these things have nothing to do with each other. Well, kind of. It's not the same at all. Mutually exclusive means they cannot happen at the same time. Independent events actually means they have to be able to happen at the same time. What's independent about them is one does not affect the other. But if you think about this, one does affect the other. Like if we're talking about the probability of you being a freshman or a sophomore. If we know you're a freshman, that sort of influences our calculation about whether or not you're a sophomore. All of a sudden we know, well, then you're obviously not a sophomore. Whereas if things were independent, like being a freshman and being in and/or, if we know you're a freshman, that doesn't really influence our calculation of whether or not you're an and/or, because it's about the same fraction of and/or throughout every grade. So those things are independent. They don't have anything to do with each other. But freshman and sophomore, those are mutually exclusive because you can't be both. So they're different. And they are showing some calculations here. If it's independent, you can go ahead and multiply them. It's mutually exclusive. This is one of the ways to decide if it's mutually exclusive. This is actually kind of the definition of mutually exclusive, is that the and ends up being 0. What would happen to the or here? This is where it gets kind of interesting. We didn't really talk about the or yet. If you want to find the probability of A or B, you could simply add them, which is a major bonus, which is why we're talking so much about mutually exclusive. It means these things don't overlap, so you can go ahead and add them. Like if you had to find the area of this entire shaded area, you can just add those two things. If add those two circles. Here, you can't add the two circles if you need the area of the snowman because you'll count some stuff extra. So that's exactly what the problem is here. That's what they're asking us to talk about here. This is the probability of A plus the probability of B. Well, that's too much. I have to subtract something. Minus that football, probability of A and B. Because if I take this whole circle plus this whole circle minus the football, which is what this is about, I will have gotten all this area exactly once. It's so clever how it all works out. Okay, one card is drawn at random from a standard deck of 52. And we're talking about diamonds and face cards. Determine if drawing a diamond and getting a face card are mutually exclusive events or not. Okay, can we get a diamond and a face card at the same time? And there are diamond face cards, right? So things like the Queen of Hearts, or sorry, the Queen of Diamonds. It's a diamond face card, and that can happen. And so yeah, both these things are true, and it's at the same time. It's one occurrence, so those are not mutually exclusive. Draw a Venn diagram. Okay, so I'll have the set of all diamonds. I'm not going to put numbers in here, I guess. Maybe I should. And the face cards at the same time. Yeah, I guess I could fill this up with how many cards are in each situation. So diamonds total, there are 13. Face cards total, there are 12. If you look at the deck of cards, we talked about that. And there are 3, oh, I made myself a really tiny area. There are 3 diamond face cards. There are 10 diamonds that are not face cards, and there are 9 face cards that are not diamonds from the other 3 suits. Determine if getting a diamond and getting a face card are independent events or not. All right, so all these are out of 52, right? If you're going to think of these as probabilities, I wrote them in here as counts. So getting a diamond and getting a face card are independent. Well, one way to do that, if you look back here at this, we do this in AP Stats all the time. If you wanted to figure this out, you could say, this is an if and only if, actually. So if you know these probabilities multiply up and make this, you can prove that they're independent. You can also think about the situation in context and go, well, is there the same number of diamonds? Like, knowing it's a diamond, does that affect our calculation of whether or not it's a face card? That might be a little harder to think about right now. But after we do this, maybe it'll be easier. Okay, so getting a diamond, we know this already. So probability of diamond and face card is 3 out of 52. The probability of diamond times the probability of face card, well, let's see what those are to see if it multiplies up and makes this. Probability of diamond is 1 out of 4, right? Because a quarter of the cards are diamond. There's 13 out of 52. Probability of face card, we already figured out, was 12 out of 52. Guess what? 1/4 of 12 equals 3 out of 52. Okay, so back to my other discussion about that. So one way to think about that is 1/4 of all of the cards are diamonds. 1/4 of the face cards are diamonds. So knowing whether or not it's a diamond does not affect the probability that it's a face card. Or knowing that it's a face card does not affect the probability of it being a diamond. Because of all of the cards, 3/13 of them are face cards. Of all the diamonds, 3/13 of them are face cards. So they do not affect each other. Calculate the probability of or. I like having the Venn diagram there because I can just go, well, it's the 10 plus the 3 plus the 9. That's all the cards that are either diamonds or face cards. And that includes both, but it doesn't include the both twice. I can't add 13 and 12 because that would count these 3 diamond face cards twice. But if I had 13 plus 9, that's gonna be better. That's 22. So that's 22 out of 52. Okay. I should probably stop there for this part.